just to get some practice. Can we determine whether this 3 by 3 matrix is invertible in some way or another?
It's not invertible because determinant is equal to 0.
Well, we don't have the determinant in our pocket yet, so let's avoid using determinants to answer this question. But after we answer this question in another way, then let's use this as a way to start talking about determinants after that.
Okay.
All right, I think we've gotten the gist of this one. And I'm muted. That's better. I think we got the gist of this one. So if we wanted to figure out whether this was an invertible matrix, we wanted to test whether or not, if we were to try to find its inverse by row reducing it against an identity matrix on the right-hand side of an augment bar, we would need to be able to row reduce this matrix down to the identity matrix. In other words, it would need to have a pivot in every row and a pivot in every column. After all, that was how we were identifying injective and surjective before, right? Injective means that a pivot has to exist in every column, and a surjective linear transformation has a pivot in every row. And so we needed to row reduce to the identity matrix in order to be invertible. But this one doesn't. We do the reduced row echelon form. It only has 2 pivots. So it's not injective because it has a column that's missing a pivot. It's not surjective because it has a row that's missing a pivot. You should convince yourself, by the way, that a square matrix, a matrix that has the same number of rows as it has columns, is either going to be bijective or it's going to be neither injective nor surjective, right? It can't be one of them and not the other, because every row can have at most 1 pivot in it. Every column can have at most 1 pivot in it. And if we have as many rows as we have columns, we can't have a non-pivot column unless we also have a non-pivot row, and vice versa, right? So it either all stands and we get bijective, or it all falls and we get neither injective nor surjective. So geometrically speaking, what's happening with this linear transformation? We can identify, for example, what the range, the inverse, the image of this linear transformation, the range. And that image is going to be the span of the columns of this matrix. And when I look at the span of the columns of this matrix, this is what it looks like. So here are the 3 vectors, which are the columns of the matrix that you just analyzed. And their span ends up being just a 2-dimensional plane. That's the image of this linear transformation. So what this transformation does is it takes all of 3-dimensional space as an input, and it squishes it down onto a 2-dimensional image. And so that's a problem as far as invertibility is concerned, because once we squish a dimension away, there's no linear transformation in the world that is going to let us go backwards and sort of re-inflate this plane into an entire 3-dimensional space. We can't do that with a linear transformation. And so one of the things that we might say is, well, does that mean that invertible linear transformations can be identified from their geometry? And the answer is yes. So invertible transformations do not zero out the volume. So this would be the way that I might say it, right? That if I have a linear transformation that takes top dimensional volume, so 3-dimensional volume in the case of this example, and the image of that 3-dimensional volume ends up being something that has 0 volume. So a plane here, as an example, right, has 0 volume. There's no volume. It has a length and a width, but it has no height, for example. So since this linear transformation, turned a volume full, if you like, 3D space into a no volume 2-dimensional image, it will not be invertible. Once we squish that dimension away, there is no getting it back, is another way to think about what's going on here, right? And so what we're going to develop after we take our 5-minute break here is we're going to develop this idea of the determinant of a linear transformation. And what the determinant of a linear transformation is it measures by what factor the volume of the image differs from the volume of the domain. So if we think about my cat example one last time for today, well, I'll probably come back to it more than once. In this,
Before to go, I'll give him for you. I'll before to go, I'll give him.
The same logic, by the way, for why we can't invert a matrix whose determinant is not 0. We can't invert a matrix whose determinant is 0. That's the same reason that we can't divide by the number 0 in the real number system. It turns out that there is a way of computing the inverse of a matrix by using just determinants, and in that determinant formula, there is the determinant of the matrix A is in the denominator. And so if the original determinant is equal to 0, we end up trying to divide by 0 when we compute the inverse. And so,
Okay, but I can conclude if a matrix has determinant equal to 0, it has no inverse.
Correct. Right. So
Yes.
invertible transformations do not zero out volume. And so what this is going to tell me is that A is invertible exactly if its determinant, if and only if, the determinant of A is non-zero. Right? So if I have a linear transformation whose determinant is 0, that means that it is squashing, it is destroying volume. There's at least one dimension along which this matrix is completely collapsing length, real positive length, down into 0 length. And so it's turning our volume into 0 volume. But as long as our matrix is not doing that, then we will have a transformation which is invertible. And so here in this cat example, we started with this transformation that looks like this, 1, 1, 0, 1. And all that this transformation was doing was taking the square, this square picture of a cat, and sort of shoving it over, shearing it is what we call it, in the positive x direction. And actually the area of the new cat picture is actually equal to the area of the old cat picture. And so in this example, here, the determinant of A is equal to 1. Since the new volume, the new area, is equal to 1 times the old volume. Right? So a linear transformation which preserves volume, or preserves area in the case of 2 dimensions, is going to have a determinant equal to 1. But another thing is, suppose that I have a linear transformation that does something more interesting, like let's say this one. So here there's kind of a lot going on. It looks like the cat that we get in the codomain here is a lot larger than the original cat that we have over here, and so we expect the determinant is going to be a bigger number, right, in this case. But another thing is happening too. Here the cat is also getting reflected. If you notice that this little brown spot on the cat's chin was on the right side of the original cat picture, but is on the left side of the cat's face in the second picture. So there's also a reflection going on as part of this linear transformation. And so where that comes in is, it comes in if the determinant of my matrix is positive versus negative. So if the determinant of A is less than 0, then A is reversing orientation. It contains an odd number of reflections in its geometry. Right? So there must be some reflection. It's like this cat is looking in a mirror, right? So we would expect that the determinant is probably some negative number in the example of this matrix, 1, 1, 2, minus 2. And that probably, because the area is getting bigger, it's going to be some number whose absolute value is larger than 1. So it turns out this particular matrix would have a determinant equal to negative 4. And we'll see why after we come back from our break. But this is the warm-up here for the ways in which we're going to be able to talk about geometry of linear transformations. We can talk about it in the whole, in sort of how does volume change, and then when we get into next week, we're going to talk about individual lengths of vectors and how do individual lengths of vectors get changed by a linear transformation. And that's when we start to talk about eigenvalues and eigenvectors and how those fit into the larger picture of geometry.